Well, thank you very much for inviting me to talk to you this evening. And yes, as Stephen said, I'm manager of the charity that looks after the status of the Geopark. And yeah, lived in the area for a large part of my working life and brought up my family up here. And I've known about and worked alongside the Geopark team through the ranger and conservation work, but only relatively recently I've come to understand there's a much work that goes into running and keeping going the status of the UNESCO Global Geopark for the area. So I'm going to talk to you about the Global Geopark as a framework for sustainable development and engagement tonight, and then Pete's going to get onto the good stuff, the geology, afterwards. So yeah, I'll just generally more about the Geopark, the work we do. And I'll sort of talk a bit about how it's structured and how that applies to the Northwest Highlands, how the Geopark system is structured and how that applies to us, and then show you some examples, the type of work and engagement that we've been doing recently. And as you'll see from this first slide, we've got a lovely 20th anniversary logo. We were first awarded the accolade in late 2004 and had our opening ceremony in September 2005, so just over 20 years ago. So established this logo for our events in the past year in recognition of all those who've worked and contributed to this quite outstanding achievement, I would say. So just quickly, so we're talking about sustainable development, thought I'd share with you this one definition. There are many out there. So this is the one which is the Geopark model is built on. Takes into consideration environmental protection, economic development, you see, and social inclusion, where these three areas overlap. And when applied to development, it could be said to be sustainable. So looking after the future for generations to come. So where did this idea of geoparks come from? It started really in the 1990s, where a group of geologists coined the term geopark because they saw that properly empowered small communities could become a real force for change, for optimism and hope, by reconnecting people and land and telling stories of how the landscape's formed, how it supports life and cultural traditions. And it's a celebration of these stories and traditions, and through this and through the way we share it with our visitors and the people of the area, we spread the message that we care and this is important to us and how it affects our livelihoods, our culture and our sense of place and home. So in the year 2000, there were 4 regions in Europe that worked together on a project designed to sort of galvanise and dynamise depressed rural areas. It was funded by the EU Commission, captured attention of the geoscience community and also of UNESCO. And they set up the European Geoparks network to address issues of geological heritage conservation, to improve public understanding of geosciences, but also to promote regional economic development. And previously they approached UNESCO in 1999 because they realised the aims were closely aligned, and that if UNESCO backed them, it would lend weight on an international level. But at that point, UNESCO realised that the movement required for this really needed to come from the ground up. So they didn't initially partner with the Geoparks project, but they supported the establishment of the network and contributed a secretariat, and the communities kind of came to this project. And by the end of that, there were 25 geoparks across Europe and China. And there are now more than 229 geoparks in 49 countries. It's probably more than that now because it's growing every time you turn around and look. And every community is really different. So every geopark's different. Some are concerned with natural hazards, such as volcanoes or tsunamis, and others look to the promotion of their landscape that helps establish more sustainable local job opportunities. But we all share a common aim, the hope that through positive education and cultural social change to build a future for our areas. So UNESCO in 2015, they recognised this sort of tremendous achievement of the growing network, and they created a new designation which is on par with World Heritage Sites. Most people have understand how that sort of system works. And so we now have the UNESCO Global Geopark. And yeah, it's hoping that the weight of UNESCO will encourage governments across the world to see the importance and support communities. We have to have certain things if we're going to be a UNESCO Global Geopark. We have to have geological heritage of global significance. We have to have a management structure. We have to make sure that we're visible so that people can find relevant information about the area. So things like signage, websites, staff to sort of engage with people. Those are important parts of the visibility aspect. And we have to network as well. So we do that locally, nationally, and internationally. So to become a geopark, you have to be functioning for at least 2 years, and it includes developing strategies on partnerships, promotion, management, geological conservation, education and information, and geotourism. And we get a rigorous evaluation every 4 years and to assess the 4 fundamental features and strategic plans. And then they report back and to see whether or not an area is revalidated or given the designation. So it's a challenge, and I know that Shetland has gone through it several times, but it's also a robust assessment and an opportunity to share the work that we've been doing. So of these strategies that I was talking about, they're linked to Sustainable Development Goals, and people are probably quite familiar with seeing this infographic. It's been around for a while now. 2015, Scotland was one of the first nations to commit to these Sustainable Development Goals. We are Global Geoparks about protection, education, sustainable economic development, and those naturally tend to be in economically, environmentally, and socially sensitive regions. So in the Northwest Highlands Geopark, we focus on number 4, which is quality education, number 8, work and decent work and economic growth, 11, sustainable cities and communities, so obviously the communities and the cities, and the 17 partnerships for the goals. And that's because if we don't work in partnership, it's extremely difficult in the area that we are in with our population, the size of population we have. So these are some of the national partnerships and local partnerships that we have. With the UNESCO UK Committee the UK Committee for UNESCO Global Geoparks. So it's a mouthful. That's a group that we have 10 geoparks in the UK now, and we link together and support each other in the work that we do. We also we're working with Scottish Geology Trust actually right at the moment now. We're doing some new interpretation panels alongside them, and I know we've worked in the past with them quite a bit. Also there's the UK National Commission for UNESCO, so that encompasses all the 65 UNESCO sites across the UK. So that's things as well as the World Heritage Sites, the biosphere reserves, the creative cities. And then we also have a more informal group at the moment, as there's just 3 of us, the Scottish Geoparks group. So see Shetland and ourselves joined recently by Aaron. So over the past 20 years, we've witnessed the transition of our geopark from just an idea, and then declared by the UN as internationally significant, on a par with these World Heritage Sites. So an incredibly exciting time. And I'd like to share with you how being a UNESCO Global Geopark makes a difference to us in the Northwest Highlands. You see here, this is sort of indicates a little bit of our management structure here. We are managed by the community. We have directors from each of our community council areas. So we have representation from across the whole area. And we've almost for over 2 decades been engaging with local people and visitors about landscape and encouraging collaboration, both within the area and externally as well. We have a unique landscape, of course, like many other places, but those that have seen it do appreciate it's something quite special, even those that have lived here for a long time, of their whole lives. And when people see a landscape like that of the Northwest Highlands, some think about the geology and some see adventure and many see the wilderness. But because our population is just 1 person per square kilometre, makes it incredibly difficult to gain sort of critical mass to grow the economy and tackle these infrastructure challenges. So under this Sustainable Development Goal number 8, decent work and economic growth, we support this through developing initiatives that bring in jobs, good quality, stable jobs, and also even a handful of new jobs makes a big impact to our area, because one of the biggest drivers to our economy is in the Highlands is, of course, tourism. And the local tourism businesses tell us they want us to help visitors to spend more time in our region and to slow down and stay a bit longer and explore what it has to offer. So yeah, these are some of the things that we do to aid that. So here we have some images of some of our exhibits at the exhibition centre, some interactive exhibits. We have signage and interpretation panels around the geopark. You can see the picture of the hut on the top right there. That's Clacktoll Ranger Hut that was built about 3 years ago now, and that's got some sort of local information interpretation in there, and can access that during the season. And we have a series of walkers guidebooks. There's a picture there of the Quirk and Assynt one. We have another 2 as well, and guided walks and apps to make the most of your visit. This is our Rockstop Visitor Centre that has our small geological exhibition, and also plenty of food and drink as well, an important stopping off point for people. So yeah, there's plenty of visitor surveys in Scotland demonstrating that people come here because of the landscape. We're particularly aware of this as a geopark, so we help people to understand and connect with the landscape in a variety of ways. We have people contacting us directly for bespoke tours of the geopark. We also have 2 to 3 week-long tours during the year, which you can book onto. Have other field trips, specifically looking at about the geology, online talks, much like this one, and guided mountain walks as well. This is an example of engaging people in a variety of ways. So this kind of crosses over a little bit with Sustainable Development Goal 4, quality education. So this was a week-long celebration of the life and work of Sir Archibald Leakey, as it says, former Director General of the Geological Survey. And we also engaged with the the schools on this as well, because Archibald Leakey was a painter as well. So we made the links with the landscape there for the art class for the local school. And yeah, carrying on with that, the sort of quality education, so working with the local schools here. And we were lucky enough to have some funding over the last 3 years, particularly from the National Lottery Heritage Fund. They funded us to the tune of 170,000 with other match funders, and we were able to employ education engagement staff. And this is some of the work that they delivered. So they had a junior ranger program for going for over a year, and this is another couple of the programs. It was a Gaelic in the Landscape project, so linking primary school children with the stories and culture of the area. Also linked up with an Irish geopark briefly on this as well. And then a Hill to Grill program, which is looking at land management, deer management specifically. So it's also then linking back to the Sustainable Development Goal 8, because it's linking high school pupils with potential areas of work that they might be interested in for the future. And this is our Explorers Club. As it says, it does what it says on the tin. It engages primary school children with exploring their geopark from the beaches, the woodlands, everywhere. Yes, and that's just a quick whiz through of some of the examples, which our geopark is benefiting local communities and visitors, and collecting local initiatives to the national and international strategies. And I'm sure there are many more examples like this across Scotland's geoparks. So yes, thank you very much. And yeah, there's a few of our acknowledgement of our funders. They were our main funders from the last few years at the bottom there. Thank you.
Thank you very much, Fiona. I wonder if there are any immediate questions for Fiona before we move on. If you wish to put your hand up electronically or otherwise, or just open and speak. David, you need to unmute, David.
Is that any better?
We can hear you now.
I just wanted to check that Torridon, is that a bit further south than the geopark? It's not included in the geopark.
It is a bit further south, yes. It's outside of our boundaries, but it lies within the Westeros UNESCO Biosphere Reserve. So a kind of one of our sister designations just to the south.
Thank you.
Okay. It seems like a very active program that you have there, particularly struck by economic development. I mean, how do you measure your impact?
Measure impact. That's a good question. In terms of, well, we were reporting to our funders the amount that we spend locally from the funds, so we monitor that. We're looking at obviously how many jobs that we have created and hope to maintain into the future. Unfortunately, like I said, we've had 3 folk. They were just part funded, so funded for a part of the time because of it was just project funding, so not been able to continue with those. But that's what our aim is to grow the organisation. So we're always constantly looking to do that.
Thank you very much. If there's nothing else, then thank you, Fiona, and we can now turn to Pete. And Pete, you're going to tell us a bit about the geology.
I will do that. Yeah. So I had a little bit of trouble screen sharing, so we'll see in a minute whether it works. Okay, hopefully it will do. I was just going to add to the answer from your last question there, actually, Stephen, that we can see how many people we are specifically attracting into the area for the geotours and so on that are coming just for that. So you have a reasonable way there of measuring a spend as well, on how many bed nights people are coming for and so on. We have the North Coast 500 at the moment, which I don't know if all your members know about, but it's a racetrack basically that
Yes.
and that kind of displaces some of the more traditional visitors that we've had in the past, because people tend to stay just one night in each, and that can disrupt the sort of accommodation patterns and so on. But we're hoping it will mature at some stage. But yeah.
So you could say it gets in the way at the moment.
It's a double-edged sword, I guess.
Yeah.
Probably. I mean, it's bringing more people in, definitely. We hope to bring people that that see the area, like certain aspects of the area, and want to come back for longer, I think, rather than just whizzing around. We get lots of camper vans as well, which can cause difficulties on our single track roads. But so yeah, there are pros and cons. Like most things in life, there are pros and cons, I think. So
Yeah.
Okay.
It gives us an opportunity to capture people that actually probably wouldn't be looking at the geology. So people coming off the road into the cafe specifically for that, and may not have ever heard of the Geopark before. So it gives you an in with different kinds of audiences. So yeah. A pro.
Okay. Let's turn from the modern to the past then, Pete.
Yeah, okay. I'll see if I can screen share here. Let's see what we can do. Oh, okay. I said it might take a minute. Yep. Yeah, can you still hear me? I'm having difficulty screen sharing here, I'm afraid.
Yep, we can hear you, Pete, and it did work before, so I'm confident.
I seem to have lost the screen sharing button on the for some reason again. Let's see.
If you hover down, it kind of comes up, because mine disappears, and then
Get
if
in
you
there.
hover over the bottom bit.
Let's just see. I think we get in there.
Well, while you're doing that, Pete, I'll just say that it's really great to see just how much the Geopark in Northwest Highlands is achieving. It's really, really nice to see. And one of these days, hopefully, I'll get there to visit. Yep, that's come up now.
That's okay.
Yeah.
It's not moving on at the moment, but I had that problem with it just now. So, well, I'll maybe start talking and tell you a bit about it, and then hopefully it will move on. But we'll see what happens. Okay. So yes, the geology. Then you've got to have world-class geology, basically. So this is a simplified geological map of the Geopark area. The red line. I don't know if you can see my cursor. Can you see the pointer all right?
Yes, we can.
Yes, that's fine.
So the red line around the outside is the boundary of the geopark. And as you can see, it's kind of defined mostly on the coastal area, just off the coast. The eastern boundary is a little bit east of what we call the Moyne Thrust Zone, which I'll tell you a little bit about in a moment. And it cuts off actually before it gets down to Ullapool. So Ullapool's not actually in the geopark. So the southern boundary just there, as you can see, and Ullapool's just off the bottom there. So it's 2,000 square kilometres, as Fiona was saying, with just over 2,000 adults in it. The geology then, we've used in the simplified map here a sort of a colour legend down the side just to divide them up for you a little bit. The really significant structure in the geopark basically is this area of black lines with the triangles on, which is a thrust zone. It's referred to as the Moyne thrust zone. So the thrusts are low angle faults basically, and it's where the rocks on the right here, the straw coloured ones, which are referred to as the Moyne rocks, have been pushed up and over the rocks over on the left hand side. So it's a major fracture basically in the Earth's crust. It formed during a mountain building episode during the Caledonian mountain building just over 400 million years ago. But I'll take you through the geology in terms of the order of age, basically, of the rocks. So to start off with, we've got the Lewisian gneiss here, the pink rock, which, as you can see, actually occupies a fair amount of the surface of the geopark. It's at the base. It's the oldest, so it's. I know you've got a little bit in the Shetland Geopark. This is age-wise, it's just over 3 billion, so just over 3,000 million, something like that. It was really metamorphosed quite intensely just under 3,000 million years ago, so about 2,800 million years, something like that. And it's a very complex rock. It is a high-grade regional metamorphic rock, so some of it we could call a granulite. It started off life as igneous rock. So it started off life probably as sort of basalt lava flows with granite intrusions and so on into it. And then it underwent its high-grade regional metamorphism. It's been down to a depth, I suppose, of the order of 25 kilometers or maybe even further down into the crust. So you can imagine really high pressures and temperatures at those sorts of depths. Then on top of that, we've got this sort of kind of orangey brown rock, and this is the Torridonian. The Torridonian is a sedimentary sequence. It consists of conglomerates, sandstones, a little bit of mudstone as well. It's in terms of thickness, it's probably getting on for about 5 or 6 kilometers thick when you added all up the total thickness of it. There's not a lot of it left now. It used to, of course, extend right across the whole of the Lewisian gneiss area, but it's mostly individual outcrops now. We've got some of the mountains down in the south here, if you can just see the cursor moving, where effectively you've got an island of Torridonian now sitting completely on its own, and you can walk around the base of it. This is the mountain Sullivan down here. You can walk right around the base of it on the Lewisian gneiss. So it used to be a continuous sheet at one time. Age-wise, about 1 billion in round numbers, 1,000 million. And it was deposited by rivers. So it's mostly a river sediment, a fluvial sediment deposited onto the eroded Lewisian gneiss. Then on top of that, we've got some Cambrian rocks. So in this simplified map, what we have is we've got these dark greys. These are the first of the Cambrian rocks. The Cambrian rocks, and actually they go a little bit up into the Ordovician, are marine sediments, pretty shallow water marine sediments. So the dark grey ones are what we call quartzites. So they're quartz sands, quartz cementing, really hard sedimentary rocks which resist weathering quite considerably. They do frost shatter a little bit, but they don't really break down to provide you much in the way of nutrients or anything like that. So and then the other Cambrian rock that we've got in here then is the limestone, and the limestone is in blue. It's referred to as the Durness limestone. So up here on the north is an area, Durness, and there's a little triangle of limestone up there. But there's also some down here in the kind of thrust areas as well. This is the Ascent area down here, Inchner Damp, quite a lot of limestone down there, and some a little bit further south down here too. So that sits on top of the quartzite rocks. and is shallow marine also. The sedimentation seems to have stopped partway through the Ordovician. There was a sort of continuous carbonate deposition through from the end of the Cambrian through into the Ordovician, but it seems to have stopped partway through the Ordovician, and it looks as if that's the time in which the mountain building phase commenced. So the sort of what we call the Caledonian mountain building commenced at that time, and the land was lifted a little bit, and that seemed to stop the sedimentation. During this time, during the Cambrian, we were on the sort of the southern shores of a large continent area with a very deep ocean called the Iapetus away to the south. So what's now England and Wales and Ireland was part of a totally different continental block at that time. We were part of a continental block that had Northern Ireland on as well. Also, other areas further north like Canada and Greenland and so on. So it was the kind of the beginning of that mountain building phase which stopped the sedimentation and then caused the huge mountain building phase and the thrust faulting that I was talking about there. During this mountain building phase, there was some melting as well. So these sort of red pockets that you can see down here are fairly large intrusions of sort of cyanites. So there was melting taking place at this destructive, because it was a destructive plate margin that we were close to at that time. So the magma was being produced and coming up into the crust. The Moyne rocks over here, then, our fourth group of rock, at one time were sediments, so they were sort of sandstones and mudstones. They've undergone a bit of regional metamorphism before even they were thrust up on top of the Cambrian rocks along this Moyne thrust zone. Now, I'm in trepidation and I press this button as to whether it's going to move on or not. So let's see what happens. No, it's not moved on. Okay. What can we do?
Pete, is it in the Google Drive? Because I could find it.
It's in the Google Drive, yeah. Mm-hmm.
It is.
It is,
Because
yeah.
I could see if I could find it and then share my screen. If that was any.
I have had this problem before, that it never moves. No problem with it moving on at any time until I'm locked into Zoom, and then it doesn't move on very easily. At the beginning of the evening, it didn't move on, and then it did move on. Okay. I mean, I could come out again and see if that does anything.
Could you just go back to like out of this slideshow bit and into just into your PowerPoint?
Yeah. Okay. I'll stop sharing then. Yeah. Okay.
Again, just while you're trying to do that, it's interesting listening to what you're saying, because it is, so much of it is quite familiar in terms of Shetland and the Lewisian and the Moyne thrust and the intrusions. And I guess the big difference is that you guys have some of the Torridonian sandstone, which
yes.
we don't.
Okay, I've got a PowerPoint version now here. So let me give that a go and see if that will do anything.
It's screen sharing. Yep.
Okay.
Looks good. Yep.
Okay, it's moving. Okay, great. Okay, PowerPoint version then. It's just the same. This is the succession then. Lewisian down at the bottom, if you can see my cursor there. Torridonian rocks here, coming up into the Cambrian marine sediments here. The quartzite, the pipe rock. Pipe rock is a burrowed version of the quartzite, so it hasn't got body fossils in it, but there are lots of vertical burrows in it, so it's been called the pipe rock. There's a couple of other thin members here of other lithologies, other sedimentary rocks, one called the Fucoid beds and one called the Saltarella grit, and I'll show you those in a minute. And then on top of that, the limestone. Okay, to try and get a bit of an idea as to what's happening 3D, I've used the BGS viewer for the mountain of Cognac, and it takes a little bit to get your eye into it. But what you're looking from up high down along the length of Cognac, the ridge of Cognac. These are the sea out in the distance here. And you can see the Louisian gneiss, the pink Louisian gneiss running around the bottom here, and the Torridonian sitting on top of it, forming the bulk of the mountain. I wanted to point out a couple of things to you first of all. The very bottom, and I'm not going to go into the formation names or anything here, but if you look at the very bottom of the Torridonian, you see how irregular the bottom surface of the Torridonian is, how it's sitting down in some valleys in the Louisian here, and there are some higher bits, some sort of hills in the Louisian just here. And the reason for that is that the Louisian was eroded in a land environment, so it was quite an irregular surface that the Torridonian was being deposited upon. So these are some of the formations of the Torridonian forming the bulk of the mountain here. And I think to give you some idea of the scale, Cognac is about 2,500 feet, I suppose, something like that. And then sloping off the eastern side of Cognac is the Cambrian rocks. So this is the quartzite, the basal quartzite, and this is the pipe rock just here too. And over in the distance, you can see still the Louisian, where all the Torridonian and the Cambrian rocks have been eroded off. And just over on the right here, you might just be able to see the basal quartzite and the pipe rock and so on again, sitting on top of the Louisian. No Torridonian there, just sitting straight onto the top of the Louisian. Okay, what do these rocks look like then? This is fairly typical of the Louisian, although as I said, it's quite a complex, quite a varied rock. It tends to have quartz and feldspar rich layers in it, and it tends to have pyroxene and amphibole rich layers in it. Quite typical of a sort of a gneiss there. Things tend to be quite sheared, quite stretched out. As I said, pretty high grade regional metamorphism. But it's not all planar like that. It's not all flat like that. So we can, for example, see in this little stack here, C stack, see the very tight folding that we've got. This is at a place called Achmelvich. So, you know, these rocks were buried very deep, behaving in quite a plastic manner because they were quite hot, under quite high compressional forces, and really producing very tight folding, sort of within the foliation planes, basically. This is another piece of Louisian gneiss, and I put this one in just to show you how varied the gneiss can be in quite a short distance here. So, for example, over on the right here, over on the left, we've got some fairly finely layered Louisian. Quartz rich layers, the lighter ones, the amphibole pyroxene rich layers, and you can see some sort of fairly intricate folding in it, and overall a closure, a fold closure. Then down here we've got some much more blocky, sheared out sort of parts of the gneiss, and then we've got a body of basic gneiss over here in close proximity. Doesn't appear to be deformed enormously. So, you know, within a very small space then, lots of different types of gneiss, if you like. This is further north, and it's Louisian. It's part of the Louisian. Again, looks quite different. You know, here we've got an area of basic or mafic parts to the gneiss. There are some granite type intrusions into it. You know, a lot of potassium feldspar in here as well. Still a bit banded. You can see some of the banded gneiss there too. So looking quite different from the last couple of pictures of gneiss. There's some dikes intruded into the gneiss. They're referred to as the Scourie dikes. The type dike is at Scourie, sort of in the middle of the Geopark area. And the sides of the dikes, there's one wall of it just on the right there and one on the left over here. It's jointed quite differently from the gneiss on either side, and the seas tended to excavate it along some of the joint planes. So it's not unusual to get trenches going across the landscape in the Louisian where these dikes have eroded out. They're not really metamorphosed at all themselves because they were intruded after the main metamorphism phases in the Louisian. There are some basic mafic dikes, but there are also some ultramafic ones, and they tend to erode out even more easily. And this trench that you're looking at on the bench was sort of, it's taken within a dike. So you've got the walls of the dike on the left and the right sides of that little cove. Okay, this is that mountain I showed you just now, Cognac. In the foreground is the Louisian. So this sort of hummocky ground down here is eroded Louisian. And here is the Torridonian sitting on top of it. And that surface of the Louisian that we're looking at is pretty much the way it was before the Torridonian was deposited on top of it. So the Torridonian has since been stripped off and is almost leaving us with a paleo landscape. So hills, little valleys and so on. It would have been modified a little bit by recent glaciations, there's no doubt about that. But I think we're probably looking at pretty much mirroring the landscape that was buried by the Torridonian. Contact, this is Louisian. This is the foliation in the Louisian, pretty vertical as we're looking at it there. And here's the unconformity with the bottom part of the Torridonian. And you can see there's some blocks of Louisian gneiss in it there, quite angular blocks in it. So you know, that contact there, that unconformity in there, then represents a huge part of the Earth's time missing. You know, if the Torridonian is about 1,000 million, something like that, and the oldest part of this is at just over 3,000 million, although it's been modified a little bit since. You know, that time gap missing in there, you could say is of the order of 2 billion years, 2,000 million years. So, about half the life of the Earth, in fact. It's a big chunk of time to be missing. I know you've got some rocks in that time frame in Shetland. Here's a different view of that unconformity. Louisian on the right. This is an old scree slope in the Torridonian coming down to where this gentleman's standing just here. And the contact between the two is pretty steep now. It wouldn't have been that steep when it was formed, because obviously a scree slope of that angle isn't stable. So when it was formed as a scree, it would have been a more gentle slope on it. The tipping, it's been tipped up further since it was formed. Some places the contact between the two is really chunky conglomerates. You can see some big, all these are Louisian boulders basically. Some are a bit rounded, some are very rounded, have travelled a bit further. So the nature of the unconformity is different in different places. This is the Torridonian on a hillside. This is actually in Loch Broom. And these ledges that you can see running across the hillside with a bit of dip on them are the bedding planes of the Torridonian. The gullies, incidentally, are eroded out along fault planes. The streams find it easier to cut their way down through fault breccias to hoik them out. So these there and these kind of ridges you can see running down here are all fault planes basically. That's a bit of a close-up of it. A bit pebbly, as you can see. Those pebbles are fairly rounded. The bedding, the normal bedding is pretty much horizontal as we're looking at it in this photo. But you can see the current bedding in it. So this is bedding formed by flowing water, by rivers. And as we're looking at them, pretty much flowing from left to right. You can see these sloping sets on them here. And the sequence is the right way up. I can tell that because the way they slope, they kind of curve away at the bottom here, but they're truncated at the top. And that's what happens in cross bedding. Smoothing sandbanks deposit sand on a slope, but then the moving water erodes off the top of those slopes. So they kind of truncate when the next bed is deposited on top. As I said, there's some lake sediments as well. So here's some mud cracking in it. The darker material is the mud. The lighter is some sand. So what's happened on the surface of the lake muds is they've dried out. They've cracked up basically, and then the next influx of sand has dropped down into the cracks and kind of is highlighting the cracks for you basically. So these lakes in the Torridonian were kind of seasonal by the looks of it, and dried out on a kind of almost probably on an annual basis. Ripple marks, so there was shallow water, there was wave action. These are symmetrical ripples, so there was wave action in the lakes. Little bit of mud on the left here, mudstone, finely layered mudstone on the left. Oxygen in the atmosphere, you can see how red most of these beds are. So the iron in them has been oxidized basically, so there's free oxygen in the atmosphere. Interesting, there's a layer there which is a little bit lighter green in color, and that's a different state of the iron. I think that's ferrous oxide, I think, in there. So maybe not quite so much oxygen around, but sometimes the oxygen in the sediment kind of gets extracted from it, so it may not be a primary feature, but definitely oxygen, free oxygen in the atmosphere. And these are the things that were releasing the oxygen into the atmosphere. So these are fossilized cyanobacteria. It's difficult to call those stromatolites, but I think they probably are stromatolites, yes, if you want to call them that. So it's more of a mat, a cyanobacteria, algal mat. So all these little crinkles in it here are layers of what are fossilized cyanobacteria. They're not continuous layers because the layers in the bottoms of the lakes dried out, cracked up, and you got the mud cracking. So this nice one in here is truncated to the right by a mud crack, and this one lower down you can see a bit of bacterial growth in there, but you've got another mud crack coming down through it, and sand has dropped down through the crack there, so that they're a bit disrupted basically. But it's cyanobacteria by this time, this is 1,000 million years old or thereabouts. Cyanobacteria have been at it for a long time. They've been at it for about 2,000 million years, 2 billion years by that time. So they started to release oxygen at more or less the same time the Lewisian was being formed. That's the sort of the oldest fossil cyanobacteria that have ever been found in the Earth. But they've been at it long enough to produce free oxygen in the atmosphere by this time anyway. There's a strange layer in it, in the Torridonian. It was interpreted as a volcanic mud flow, but it's now interpreted as a meteorite impact ejector. It's called the Stack Fada member. And what you're looking at here is a fresh piece of it. And what it's made up of is devitrified glass fragments. So all these little green bits used to be glass. So molten, in other words, molten fragments. There's a bit of Lewisian in here too. That's a bit of Lewisian. There's some bits of Torridonian mudstone in there. There's quite a lot of red sand round about it as too. So it's quite a mixed deposit. But it has got these devitrified glass pieces in it. So that's why it was originally interpreted as a volcanic mud flow, because it was thought these were bits of volcanic glass. But on close inspection of this material, it's got things in it which you wouldn't expect necessarily to have in a volcanic mud flow. So there's little bits of an element called iridium in it. There's shocked quartz in it. Some of the minerals called zircon are really quite shocked in it, and it's got a mineral in the kind of shock layers, shock lamellae within the zircons called reedite, and that really only forms at incredibly high pressures. So really only forms at with impacts like that. So it's interpreted as an impact ejector now, a 1,000 million year old ejector. This ejector picked up things as it flowed across the surface. This is a big boulder of Louisian. It's very rounded. I think it must have been sitting in a river course or something as the flow went over, picked it up, carried it until eventually it dropped it. And it's all ejector material that's round about it, just like the last photo that I showed you. This is it actually at Stackfadder. And this layer up here on the left is the flow. And there are some bits of the flow coming through here. But what you can probably notice is the pieces of Torridonian sandstone are kind of all tipping off in different angles. There's a piece with a dip on it coming down here. There's a piece with a dip going that way. There's a piece up here which comes along and dips down. There's an isolated chunk here which has actually got a bent back end to it. You'll have to take my word on that, but close up the bedding comes this way and bends right back on itself there. So it's been carried. And there are also in it some of these accretionary lapilli, which look a bit like little Maltesers. And this is material that was being carried in the flow as a very fine ash type material, and it's kind of aggregated together as it was carrying and then being dumped as part of the ejector. Okay, the Cambrian rocks. This is the mountain called Canis, being nascent as well. Down here is the Torridonian. Probably see a very clear piece of Torridonian there horizontally. And this is the Cambrian quartzite sloping off, forming the long ridge of Canis here. Quite a lot of scree, quartzite scree. So the quartzites do frost shatter relatively easily, but sitting on top of it. And there's obviously an unconformity between them because you've got an angular difference. Torridonian coming this way and the basal quartzite, the Cambrian, going that way. This is the pipe rock. So these are some of the burrows, vertical burrows in it. Here the quartzite's got a little bit of redness to it. These were chosen, actually, this is in the wall at Knocken, for those of you that have ever been to Knocken Crag National Nature Reserve. It was chosen for there because the sand's a bit pinker and therefore you can see the pipes quite nicely. Otherwise you get white pipes in white quartzite and it's quite difficult to spot them. Like here. This is the top surface of the pipe rock, and all those little round circles that you can see are the tops of some of the pipes. So you've got some idea of how much of that sediment, that beach sediment, it's probably intertidal when it was formed, have been reworked. You know, all those circles are reworked parts of the sediment, basically. So there's probably more reworked sediment there than there is unreworked. But there has been found recently a very strange body fossil in the pipe rock, and it's this star-shaped fossil in here. It's called Sphaconopsis, and it looks as if it's probably related to the Ediacaran in some ways. Not really certain what it looks like. Our administrator, the Geopark administrator, has been working on some reconstructions recently. She's an artist as well. So she's been working on some reconstructions, paleo reconstructions with Oxford University on this, which will be available soon. There's some trilobites in there. This is the Fucoid beds. This is an Olenellus trilobite. I think it's Lapworthi probably. These are exoskeletons of trilobites. That's viewing the undersurface of one. And that's viewing the top surface of one. See that the arc-shaped eyes here, the segmented body, and the head shield, the Keflon up at the top there. It's usually only the head shields, the Keflons, that are preserved. Usually the segmented body breaks up. So you're lucky if you find a head shield, but you're even luckier if you find the whole trilobite. This is what was the bed of the sea during Fucoid bed times, when the trilobites were scuttling around, basically, probably slightly down into the sediment. And these, I think, are probably feeding trails from the trilobites. There's all sorts of burrowing things happening in here too, but these little fine lines, I think, are probably trilobite feeding tracks. This is the grit on top, the Saltarella grit, which is really another quartzite. And these are the Saltarella, which I'm pointing to there. They're little cone-shaped fossils. There's one there you can see inside the cone. This is the Mendon. They look circular. They could have been a gastropod. I don't think it's 100% certain what they were, or at least I'm not 100% certain what they were. Then on to the limestone. This is Elfin in the middle of the geopark, and you can see the green grass area there. So these are the limestones. These are the Durness limestones low down here. So in the limestone areas, we get nice fertile pieces of ground, nice neutral soils, well drained. So the crofters quite like them. So anywhere you get a bit of limestone, you'll get crofters on it. But you might notice these hills in the background here. These are a couple of our Monroes, actually. This is Conival and Benmore Ascent in the background here, and Braebag here. These are made of a variety of rocks, but quite a lot of quartzite in there. You can see from the scree slopes. But the odd thing is, on the face of it, when you look at it, they're physically a lot higher than the limestones. And the limestones are younger than the quartzites, which sit on top of them. And there are thrust faults, can't see them from here, but there are thrust faults above the limestone and below the quartzites. This is Conival from Loch Assynt, and these are quartzites and other sorts of rocks making up Conival. And this is the limestone down at the bottom. Durness limestone down at the bottom, younger than these rocks up on top of it. So it's a thrust fault coming through here. I think the thrust fault's kind of at about this level here somewhere. But you also might have noticed the folding. Can you see the folding down in the limestone here? If you follow the cursor, you've got a bit of an asymmetric, almost overturned fold actually here. Oh, it's just moved on. Let me move it back again a minute. Overturned fold there, coming down there, going on there. And you've got a little infill in a syncline here too of limestone, a little overturned syncline in there. Close up of it, you see the bedding in it now. So one limb going up, vertically dropping down here, turning and coming up over there. And there's the little syncline infill into this syncline here. And these are the older rocks up above. There's actually a bit of Lewisian gneiss up there too. Lewisian gneiss and quartzites and things up there. Okay, there's a lot I could say, but in terms of the thrust faulting, but just quickly a little bit about glaciation. So last 2.5 million years, obviously, as with Shetland, heavily glaciated. This is a lodgement till. This is a till from under the ice, basically. You can see some of the clasts in it, but a lot of very fine clay material in there as well. A lot of grinding up going on. Striations. This is striations on the top of Torridonian, actually. You can see very fresh looking striations. The reason they look so fresh is that the moraine that was dumped on top of them is only just being eroded off today, basically. So this is the surface as it was glaciated probably 20,000 years ago, maybe a bit more. We've got erratics. This is a Lewisian gneiss erratic. You can see a bit of folding in it there, sitting on Torridonian. Torridonian's got a dip on it like that, about 20 odd degrees right to left. Sometimes the erratics are quite useful for working out the track of the ice. If you can find your piece of gneiss where it's come from, then you've got an idea as to exactly the trail of the ice. This is a LiDAR image. So LiDAR is a kind of slightly ground penetrating radar, if you like. It can penetrate through vegetation so that you can see the solid rock underneath. And what we're looking at here, this is Loch Broom. This is Ullapool just in here, sitting on a raised beach. This is Ardmere, if anyone knows where Ardmere is, and Isle Martin's just there. And these grooves that you can see cut across here, looks as if they've been cut subglacially underneath fast-flowing ice, probably by meltwaters, high-pressure meltwaters carrying sediment. They're referred to as mega grooves, and you seem to get them only in the areas where you have fast-moving ice. Some places the ice effectively sticks to the land surface, doesn't move very much at all. Others it's moving pretty fast. So this is one of the fast-flowing areas. This is not bedding. This is not geological, not foliation plains. This is moyne actually here, but the bedding in the moyne is running more or less north-south here. So these are all the lines that you can see there are cut by ice. This one takes a little bit of getting your eye around. It's Loch Broom. This is Coiach, if anybody knows Coiach here. Ullapool's just off the bottom right. This is the other side of Loch Broom. And what the colours are showing you is the depth of water in Loch Broom. So what you can see is actually the pristine glacial environment before the sea level rose and flooded it. So what we've got is some of those grooves that I was talking about. There's some here. This one's marked A and B. Some of the grooves going that way is another one just in here. There's some over deepened basins, not unusual in glaciated areas for them to really cut down deep in some places. We've got some gas pock marks. This is gas escaping from the modern day sediment as the organics decompose in it. But the reason I put it on there was so you could see the retreating terminal moraines. So after the last glaciation, if you look up in the top left, can you see these red areas, red ridges running across? So that's shallow water, and these are retreating terminal moraines as the ice retreated time after time up Loch Broom. And these are probably about 20,000 years old, something like that. We're almost at the end now. I put this one in so that you could see the raised beaches that we have locally. There's a kind of a level here. There's a lower level down there. And if you've been to Ullapool, you'll know that Ullapool has something similar. It's got two raised beaches, an upper level and a lower level. They don't tend to be cut very much into solid rock, but they tend to be formed from glacial outwash material. Although there are some old sea cliffs just at the back here. So quite recent features. So we've got isostatic adjustment here. So the land has been rising, probably still is rising a little bit actually. But the other feature I put it in is so you can see the Moyne thrust. You can't go away from a talk from the Geopark, Northwest Highlands Geopark, without seeing the Moyne thrust. So, it starts there on the skyline and runs diagonally across here. Oh. This is Moyne schist up here, Moyne material, and it's being thrust over Torridonian here and Lewisian, which is caught up in the thrust faulting. So often the Moyne thrust zone is not a single plane, but a sort of a complex zone of thrust faults. And the final one, peat. Can't go away without mentioning peat. Plenty of that in Shetland, I know. And some of the old trees, stumps here growing in the bottom of the peat. This root system, I don't know what this is. Don't know if it's a Scots pine or quite what it is, but the roots basically penetrate down into the to the moraine, and then the peat is built up round about it basically. So these tree stumps are probably the order of about 5,000 years old, something like that. And I'm sure if you've cut peat, you'll be used to finding these down towards the bottom of the peat layer. And I think that's it. Yeah.
Well, thank you very much, Pete. That was a grand whistle-stop tour of
It was
3 billion years of the Northwest Highlands. So thank you very much.